So thanks, Alex, for the introduction. And good afternoon, everyone, or good evening, depending on your time zone. So my name is Dongmin Yang, and I'm a senior lecturer in composite materials at the University of Edinburgh. So in this presentation, I'll talk about our recent work on 3D printing of curved continuous carbon fiber reinforced epoxy composites. So some of you may be aware that most of the commercial composite 3D printers use a wonky fiber tool in a thermoplastic matrix, for instance, PS6 thermoplastic. The filament is usually made in a cylindrical shape, and the brass nozzle is used to avoid the excessive wear and also reduce the damage on the fibers. The nozzle usually has a conic outlet, and each size is much larger than the filament. So when printing in a straight path, the nozzle presses on the filament and changes its shape to a strip. This process causes a non-uniform pressure distribution and therefore fiber misalignment in the strip. So the fibers could also be split into multiple toes due to the large tension at the bottom of the strip. Substantial voids may occur due to the high melt viscosity of the PS6. Because the filament is much smaller than the nozzle, so actually it's wobbling the nozzle, makes it more difficult to achieve accurate print passes. And these issues become more severe when printing curved passes. Fiber twisting and fiber folding usually happen at the corner, which could lead to inconsistent toe widths and inaccurate placement position. The friction between the nozzle and the filament would stretch the strip and cause toe debonding. And this could block the lax deposition on top and eventually terminate the printing process. So in view of these challenges, and funded by the EPSRC SimComp Hub, we are looking at a different approach to print continuous carbon fiber composite. So instead of using the thermoplastic, we use powder-based solid epoxy, which has a very low viscosity to reduce the voids, and it's easy to store as compared to other liquid epoxy. So to address the fiber misalignment issue, we also develop a rotational printing system together with the use of a special print nozzle. So first, the carbon fiber reinforced epoxy filament is manufactured using a tape line previously developed by Corning. Corning has already introduced the tape line, so I'm not going to repeat that. So as the filament is quite small, we use the infrared heating instead of the dual contact heating, which is quite effective to produce filament with a good circular cross-section. We then tested the filament for 3D printing of UD laminar and laminate. We found that after consolidation, there is a very good wettability and bonding, and also there is no noticeable voids present. The fiber volume fraction in the filament can be easily controlled by adjusting the electrostatic powder deposition process. So up to 60% fiber volume fraction can be achieved. And that could give us the flexibility to produce bespoke filament for specific applications. We also developed a special nozzle with a rectangular outlet in contrast to the conic outlet of the Mark Forged nozzle. So as you can see from the sketch, the new nozzle would give a more uniform pressure distribution on the printed strip. But to accommodate this special rectangular nozzle, they modified a FDM 3D printer and introduced an additional rotation when printing a curved path or turning around a corner. So basically, we use a motor to rotate the print head and make sure the nozzle outlet is always perpendicular to the print direction. So we then tested both the straight and curved single print passes. So as you can see, as expected in the straight print pass, the fibers are almost perfectly aligned with the print direction. The shape of the printed strip is also quite consistent and accurate. In particular, when we print the curved pass with a rotation, there is no obvious fiber twisting. The friction between the nozzle and the filament induce a toe shifting, which seems to mitigate the fiber breakage and the fiber folding, but still maintain a good printed shape. So to demonstrate this rotational printing system and also the powered epoxy filament, we then printed a curved fiber composite. So here we consider a composite plate with a hole and a unit extra tension. So what we do here is we first use finite element analysis to identify the principal stress trajectories in the lead polymer material, and then we set out the fiber placement along the stress trajectory lines. So then G-code is generated by synchronizing the rotation of the print head with the print path, so that a good fiber alignment is achieved at every single position in each pass. And similarly, a laminate can also be printed by controlling the fiber placement in each layer. To take this technology further, we also developed a second prototype, which is more robust and universal for different types of filaments at different size. It is also suitable for printing carbon fiber reinforced thermoplastic composites. On the other hand, we managed to produce some slightly larger filament using the 3K fiber tools. The new printed prototype will allow the switch between different filaments, so we can achieve a good balance between the high print quality and the fast deposition rate. So there will be more work coming out very soon. So, okay, I guess that's all from me for now. So thank you for your attention.